My name is Hironori Yasukawa of Hiroshima University, Japan. I'm chairman of the Specialist Committee on Monitoring the Waves. So then you can see the name of the member of the Specialist Committee. Dr. Tera Ruiz from HSVA, Dr. Milano for BSHC, Dr. Sun, Hyundai Heavy Industries, Dr. Kim from CRISO, Professor Gu from Shanghai Jiaotong University, Professor Duan, Harbin Engineering University, and Dr. Steinman. But he left in 2019. Okay, that is our task. So then you can find some keyword that related to our task. The state of the art. The state of the art based on the topics about monitoring the waves. So then we have to make the guideline for benchmark tests on maneuvering in waves. So then also find the keyword of minimum power requirement. So then also find the minimum power requirement and blah, blah, blah. Originally, we planned to add the results of the SIMA workshop, but we did not mention it because it was postponed due to the influence of the coronavirus. So main topics in my presentation is as shown here. State of the art of the prediction method of ship maneuvering waves and minimum engine power requirement. Based on these results, last we describe the conclusion and the recommendation. The state of the art of the prediction methods of ship maneuvering waves. So in our report, you can find in the 5 sections. First, experimental method. The second, the numerical method. Third, steady sailing performance and the maneuvering limit, wind and waves, wave effect on ship maneuvering in shallow water. Fifth, additional aspect of maneuvering simulation waves. But this time, I'd like to skip these topics. Experimental method. Experimental method was composed of 2 types of the test. One is a free-running test in the waves. This main purpose is capturing the motion in waves of the ship. The second one, the captive model test. So this one is the main purpose, capturing the force and the moment acting on the vessel moving in waves. The purpose is quite different. Free-running test in the waves. So then nowadays we can find a lot of papers. In tests in regular waves and also tests in irregular waves. Of course, actual sea is not regular, actually irregular. But tests in the regular waves is quite useful to understand an actual phenomena about the ship motion in waves, and for checking the theoretical method, the regular wave test is really useful. In 1980, Dr. Hirano carried out the free-running test in the regular waves. Nowadays, you can find a lot of free-running tests have been carried out. In the irregular waves, 2006, Yasuka carried out the test. So now, but the number of the tests is not so many like a regular wave test. But I think the test in irregular is really important because the actual seas are irregular. Okay, here I would like to introduce the measurement system, especially for measurement of the position of the ship motion in the waves. Okay, named the total station system. Total system is a fully wireless system for position measurement. So then this system, originally, this total system comes from civil engineering field. So then you can see this figure, you can find some boats here. So then these are some, prism for position target installed this boat. This target is a basically prism. You can see that this is a photograph on the prism. So then this prism. So then this one is a camera of the total station. So then this camera can track the ship model position about the prism automatically from the side. So then this one is the photograph of the camera of the total station. So then you can find while black circle, this like an eye. So then the automatically track of the target. Then we can measure the position. So 2019, Kim to measure the position of the sim model in the waves using this total station system. So then that is the result. So you can see that the figure about turning trajectory in the regular waves. So then there's you can find a lot of turning circle. So then there's totally 6 trajectory that plotted, calm water and trajectory in the waves. So wavelength changes lambda by L equals 0.5 to 1.5. So then there's waves coming like here. Ship is approaching like here. So then the rudder, after executing the rudder steering, so then turn starts, the trajectory moves like that. So then is this trajectory trajectory in the car motor. So you can find circular turning. In the wave cases, some drifting occurs during the turning. Generally, the ship drifts in a direction different from the wave direction during turning, because the wave directions here, but drifting directions like here in the case of lambda by equal 1.0 or trajectories. In the case of lambda by 0.7, drifting directions like here. Lambda by L equals 0.5 cases, drifting directions here. So that is a really unique phenomena. So drifting direction is depending on the lambda by L. And also, the ship significantly drifts in shorter wavelength cases. This black line results in the lambda by 1.0, but in the case of lambda by 0.7, this one is the dotted lines here. In a shorter wave cases, the green lines here. Drifting distance from here to here is much larger compared with the result in the lambda by 1.0. So like that, drifting phenomena during turning, so direction and drifting distance depending on the wavelengths. So next is I'd like to show the captive model test in the waves. So unfortunately, in that case, the published papers are huge. So here, I would like to introduce the results of the wave induced motion and the drift force of a ship obliquely moving in regular waves. In oblique cases, so then in a heave and pitch, wave induced motion amplitude, the tendency, the phenomena is almost the same as the drift angle equals 0 cases, still moving. Then there are 5-degree drift angle cases, 10 degrees drift angle cases, almost the same in heave and pitch amplitude. But in a sway and roll, lateral motion, so then there's a big influence appears. Of course, in a drift angle equals 0 cases, sway is almost 0, roll is almost 0. But putting some drift angle, sway and roll appears more. So then in the case of a roll, they become quite large value in the long wave cases. That means they are existing the coupling between the longitudinal motion and transverse lateral motion in a case of oblique moving thing. This one, the added resistance results. This one is a steady lateral force and steady yaw moment results. Added resistance, the effect of the oblique hull drift angle on the added resistance is not so remarkable. But steady lateral force, you can see that in the case of large drift angle cases, steady lateral force become larger in absolute values. Steady yaw moment is also. Like that, especially in a lateral movement or some lateral steady forces, hull drift angle equal effects become remarkable. Okay, next, I will talk about the numerical method. Works addressing the topic of maneuvering can be classified in 4 main groups. Mean wave force method, two-time scale method, unified method, and CFD-based direction simulation method. Okay, first, I will describe the mean wave force method. Basically, this method is almost the same as the car motor maneuvering model. There are no changes to the car motor maneuvering model, but only mean second order wave forces are added. The mean second order wave forces calculated previously for all heading, frequencies, speed, and stored as multidirectional tables. So in that sense, mean wave force is quite simple and nowadays are widely used. Next is the two-time scale method. Two-time method, the first, we assume the maneuvering wave that's in total slip motion is expressed as a usual maneuvering motion and wave-induced motion. Because the maneuvering motion is basically low frequency, but when the wave is motion is high frequency, then we can separately treat these two models. So then the usual maneuvering model is basically same as a mean wave force method. So then we have to also consider the CTP model. Two models are separately solved. Then of course, information exchange is really important. After solving the problem, the maneuvering, so we can get the ship position, ship orientation, and the ship speed. Based on such data, so we can calculate wave-induced motion in the CTP model. So then these are such kind of the information exchange that's really important. Next is a unified method. This one is a more general formulation. So then this basically motion equation is a 6DOF. 6DOF motion equation is treated. But the problem is a prediction or expression of the forces, moment acting on the ship. Because when considering the maneuvering waves, we have to consider the first maneuvering forces such as the rudder force, propeller force, and some damping force related to maneuvering forces. At the same time, we have to consider the radiation forces for seakeeping sense, and in the wave extended force, we have to consider. Then this this method easily includes a nonlinear effect through the nonlinear fluid forces, and have to consider the second order mean forces. The rational prediction, rational expression of the force and the moment, that is a problem. But of course, this one is a general formulation is possible. So then now there are several versions. So then here we introduce the calculation example by the two-time scale method. So this one is a turning trajectory in waves. So then the rudder angle equals 35 degrees. for starboard turning. Waves coming here means beam waves. Lambda by L equals 0.7. The result in a regular waves. Red color means calculation results, trajectories. Dot in blue color experiments. The calculations to capture well the tendency. Okay, this one is a comparison of the time histories. Yaw rate, drift angle, the heave. This is a calculation of the yaw rate, calculation example. You can see the 2-time scale method captures well the high frequency phenomena. And the agreement with the experiments is acceptable. Drift angle is here, heave motion during the turning. So then there's an agreement between calculation, the experiment is acceptable. Okay, next is a shift D based direct simulation method. Direct simulation using computational fluid dynamics provides a better understanding of the hydrodynamic problem of ship maneuvering. It can solve specific local flow details around the hull and its appendage together with the ship motion. So then now the several paper are published as shown here. Okay, here I'd like introduce the results. So then you can find this one is turning in the wave cases. So then you can find some deformation of the free surface. At the same time, we can capture some flow detail, especially in the vertical structure around the ship hull during turning in the waves. Nowadays, computational time is quite huge, but I think they're really promising in near future. Okay, next, I'd like to talk about steady sailing performance and maneuvering limit in wind and waves. Okay, what is a steady sailing performance? This one is composed of 2 elements. One is average steady sailing condition, SSC, such as check helm, speed drop, hull drift angle, etc. of a ship moving straight in constant wind and waves. This value is easily obtained by solving the motion equation, steady motion equation. So then we can get as a steady solution. If we can get a steady solution at that position, we can check the course stability. So then there's a steady value SSC and course stability. So then checking. So then such kind of performance is called steady sailing performance here. This one is really useful for discussing ship maneuvering limit in the adverse weather condition. So this one is basically treated as application example based on the mean wave force method. Okay, this one is a result. This one is a steady solution with steady ship velocity, check helm, hull drift angle. In that graph, horizontal axis means 0 means the heading angle, 9 degrees the beam waves, 100 degrees the following the waves. So then we can change the weather condition from Beaufort scale 6 to Beaufort scale 10. In the case of Beaufort scale 10, ship velocity is 5 knots in the wave, head and wave cases. So then the maximum check helm is almost 10 degrees. So then this ship has sufficient has a sufficient margin for safety. Anyway, this one is the result for pure carrier. So then the maximum hull drift angle is almost 7 degrees. Based on such information, we can discuss the maneuvering limit in the wind and the waves. Next, wave effect on ship maneuvering in shallow waters. This one, really complicated problem because there is limitation more than the water depth. So then there's a wave coming. So then there's a ship motion that appears. So then the really complicated problems to deal with. So then this result was from Taylor Ruiz et al. In 2019. This one, the result lateral force, roll moment, or yaw moment. They only measured steady force and moment in shallow water in-head waves. Result shows the mean wave effect larger at low speed cases. But drift angle effect on the mean wave forces not so significant. But this experiment has some of the big restriction because they carried out the fully fixed ship model, no induced motion. In the sea keeping sense, just they carried out the test in the diffraction problem. So then I think the more work on these topics yet to be investigated. I think the more investigation is needed. Okay, next move to the minimum energy power requirement. That is the background. IMO adopted Energy Efficiency Design Index, EDI, for new ships to reduce the shipping greenhouse gases emission via improved ship design and operation. There was a concern that one of the most effective ways of reducing the EDI is simply by choosing a smaller main engine, thus consequently reducing the ship's design speed. Within IMO, a debate took place on how far speed reduction could be used to attain low levels of the EDI. As a result, it was decided to limit the use of this method of EDI reduction so that it does not lead to unsafe and underpowered ships that may lose maneuvering capability under adverse weather conditions. So then we gave the task that is address the issue brought about from IMO MEPC 71 and the following meeting concerning the minimum power requirement, including issues on maneuverability and adverse weather. Validate the level 2 simplified assessment method of the 2013 interim guideline. Okay, so then the first we introduce some assessment. Revision of 2013 interim guideline for determining the minimum propellant power. In the assessment, there are two methods. First one, the level 1. This one is a quite simple one, based on some existing database, just to put some, taking some line. So when checking this graph, okay, this minimum line is like that. So this line is, I think, too simple. So then this level 2 assessment was proposed. This one is quite straightforward. First one is have to define some weather condition. Next, based on weather condition, have to calculate the resistance, car motor resistance, aerodynamic resistance, added resistance waves, and appended resistance. Based on these results, calculate required power, required advance coefficient, required RPS, required delivered power. I think they're quite reasonable. But there is some issues in this assessment. Okay, that's the problem. First one is what is the rational adverse weather condition? The second is added resistance waves. Prediction method is no problem. How about its accuracy? Third one is a propeller load difference. Car motor results and in a wave cases, propeller load is quite different. So then is a thrust deduction T and the wake fraction changing. How should we treat this problem. At present, no conclusion have been reached, but we'd like to discuss more detail. About adverse weather conditions, of course, we can propose many kind. Okay, summarize. Okay, that is the history of the proposal. But this one is summarized and for adverse weather condition. Okay, 8 sub 1 per 3. This is a significant wave height. This one the average wave period. This one is a wind velocity. So then is a wave height is quite different. So then there's a average wave period. This is a some proposal with some range was proposed. That the wave wind velocity is here. What is the most important, most significant factor? Okay, the result is a wave height. Okay, you can see that based on this for adverse condition, we calculated some resistance component. Blue colored column the calm water power. So then the should be same. But the gray colored column is the air resistance. This depends on the wind velocity. So then the red column, that is the biggest one. This is a wave added resistance waves. So then the most important factor the significant wave height. In the cases, 7-meter wave height cases really big. Because the added resistance wave is basically proportional to the square of the wave height. So then so anyway, so what is a reasonable wave height? That is a problem. Okay, next, we want to calculate the added resistance waves. Then, of course, we need some prediction method. So then nowadays, some similar method was presented. You can find this table, you can find the program names here. You can find the 6 method. Type is some empirical based on the 2D strip method, the 3D panel method. Okay, calculation methods are slightly different. Some correction method is also different, applied and different. Okay, using this 6th method, we carried out some prediction about the KVH2 tanker. The fluid number equals 0.051. That's a slow case because in the waves, speed drop occurs. So then is okay, you can find this triangle, mark of the triangle, the experiment. Other line is prediction results. Agreement between the experiments is prediction is not so good. The larger one is here, smaller one is here, but the experiment is here. At present, any prediction method of that resistance waves, accuracy may be not sufficient. Using this the method, we calculate the added resistance waves here. Maximum one is here, small one is here. So then is the difference is big. Next is the propeller difference in the calm water and the waves. Okay, this one is there is some history. First one is a prediction of the thrust deduction factor, the new fractions, some empirical method, or sometimes we can use a tank test result. So then there's in the case of KVCC2, this value is a wake fraction equals 0.35, but the thrust reduction the rate of the 245. So then this design speed is the fluid number is almost 0.141. Some prediction method is the same order. But in MEPC 71, 72 that China proposed, pointed out, this value is changing in the depend on the propeller load. In moving in the waves, propeller load changing, speed is a drop. So then the propeller change. So then the wake fraction, the thrust reduction also changes. In the MEPC 71, wake fraction becomes 0.15. China presented. Wake fraction changed the 0.15. Thrust reduction changed the 0.1. So then this values are quite different. If we use the larger value 0.35, 0.25, the minimum power is like here. This is level. But then if we can use a smaller value here, so then the minimum power becomes large. So this difference is quite big. That is a problem. But unfortunately, at present, no conclusions have been reached. Okay, conclusion of activities. About prediction methods of the maneuvering waves. A large number of works on maneuvering waves methods have been published during this period. Experimental research remains variable and is being used complementary to numerical research. Due to technological development progress, testing irregular waves with large wave height are becoming more feasible. Direct CFD simulations of maneuvering waves were presented by several authors. Using CFD simulations, propulsion and turning motion, as well as the maneuver of a free-running model in the regular waves can be conducted. However, due to the high computational time, computational cost, and even longer time simulation requirement, direct CFD maneuvering simulation in the regular waves are still a challenging problem. Until now, the problem of maneuvering in deep water waves has been mainly treated, but the problem has been extended to shallow water. As an application example of the calculation maneuvering waves, there are many studies on the maneuvering limit of ships by analyzing the steady sailing performance. About benchmark data, this time we did not mention here, but the Simon research project has facilitated the new data for the KCS and the ONRT in the regular waves. This data is quite valuable to support the validation and the confirmation of numerical simulation method. The Simon workshop will be held this year. Minimum engine power requirement. The issues brought about from IMO NEPC 71 and the following meeting were addressed concerning the minimum power requirement. The accurate estimation that the resistance waves and the self-propulsion factors in higher propeller load condition are decisive factor for the simplified assessment. Recommendation. Update the following guidelines. Free-running model test in waves, captive model test for measuring force in waves. The basic guidelines have been already made. To improve the numerical method for maneuvering the waves, the following actions are needed. Validate the numerical method for mean wave drift forces, especially the steady lateral force and sea yaw moment, acting on advancing ship in cooperation with the Seakeeping Committee. Provide the captive test data on the hydrodynamic forces acting on the ship in the wave, such as blah, 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 for validation of CFD cooperation with the maneuvering committee. Investigate the effect of wave height on the propulsive performance and the coupling with the main engine in cooperation with the propulsion committee. No time, so this time we didn't mention about these topics. For minimum engine power requirement, validate the level 2 simplified assessment method of the 2017 Inter guideline by enhanced and comprehensive method. Thank you for your kind attention.